Hello everyone, so we are starting this video to solve the solve examples, and along with this video you will find after the video an embedded portion of what is called the basic integrals and single variable calculus and all of those stuffs. But before that, when you get to that step, or you can just check the stuff earlier as well, so that is basically the introduction and the portions which will be required in order to compromise this video, in order to understand all of this stuff what we are going to learn today, because we are basically going to solve examples, and we are going to solve examples while learning how to do this partition theory to actually do integrals. Okay, so it's gonna be a long ride, so there are going to be multiple videos on this now, and let us start. So I'll write the problems one by one, and then we can solve them and understand them clearly, thoroughly with each step. So here goes the first problem. So this is basically the first problem which we are going to do. So carefully read the problem first, and then I shall read it and explain it to you, and then we shall move on to the solution. I give you 10 seconds to read the problem and understand it. Okay, so we see the problem saying is that the function f of x comma y has been defined like this, and that we need to show that f is integrable and the integral over f over the region which the domain is defined is equals to half, and the function is a piecewise function which is 0 if x x is from 0 to half, and it is 1 if x is from half to 1. So let us do all the necessary pre-bindings first, and I shall write down the solution, then I shall explain it. partition P is composed of two other partitions, P1 and P2, and this is because we see right here that P is a partition and we need two partitions for our case, because you know the domain is 0, 1 cross 0, 1, which is the R square, so it's a subset of R square, right? Because a region here, because our integration region here is just A equals to 0, 1 squared, which is basically a subset of R square, so it belongs to R square, right? So obviously that's why we need two such partitions, and using two such partitions what we can do is as follows. L of f comma p would then be summation over all such subrectangles 0 comma s infimum of s of f multiplied by the volume of s, right? Now what we can see here is ms of f, so there are two rectangles, right? So we actually do not need to do it for each rectangle, but we can do it directly. So for the first rectangle, which is this 0, 1 by 2, the minimum is 0 and the volume is half minus 0, right? So and for the second rectangle, it is from half to 1, the infimum is 1 by 2, while this basically here it's basically 1, right? The volume of s is 1. So it becomes 1 by 2. And similarly for the upper sum, we have for 0, 1 by 2, it is 1 by 2 into 1 by 2, and for the other part it's also again 1 by 2 into 1 by 2, so it's 1 by 4 plus 1 by 4, which is 1 by 2. And so we see the lower and upper sums are equal, and therefore is 1 by 2, right? So this is basically the Riemann condition, and from the Riemann condition we understand that this is how we can evaluate this lower sums and this upper sums, right? Okay, now this is how we do this first sum. Let us move on to the next one. Let me write down the problem, and this is going to be a difficult sum, a much difficult sum than the previous one rather, so we are going to need to focus on this one. So we need to show that g is integrable and that the integrals are equal, right? This is what we need to show. So the goal of this problem is to let you know that if one of the functions are integrable and there is another function which is equal with this function, which is basically this function, except at finitely many points. When I say finitely many points, I mean for a countable set of points the functions are not equal, but for infinitely many of them they are equal, right? So when I say that, it means that the integral of those two functions are basically equal, and that's what it means to show this problem. So let us begin. We know from the Riemann condition the following things, and we are going to write that. So let me just write down the solution one by one. So first we are fixing an epsilon greater than 0, because this epsilon should be a real number. Less than epsilon greater than 2. Now, since we know that the partitions should be different for f and g, because what we understand is that g is not equal to f at finitely many points, right? So if we are going to integrate f with the partition p, then we should need another partition p prime. So we consider p prime to be a refinement of p such that So what do we mean is, we consider p prime to be a refinement of p such that for every x belongs to a, where a is the integration region with g of x not equals to f of x, so we are considering all the points x where the functions g and f are not equal, and we are saying that it belongs to 2 to the power n subrectangles, so it should be subrectangles actually, subrectangles of p prime, which is the new partition. That is, x is a corner of each such subrectangle, right? So basically for each subrectangle, so for each subrectangle S of p prime, we have we are defining this, and let me define the terms here. So these are our definitions, right? And this partition is made such that the volume of each subrectangle is less than epsilon, and you see the epsilon by 2 from here comes from this epsilon by 2, and it gets multiplied with 1 by 2 to the power n d of u minus l. So what we are trying to find here is that we are dividing the whole region into sub-regions where each rectangle has an area of 1 by 2 to the power n, because there are 2 to the power n sub-rectangles, so each one will have 1 by 2 to the power nth of the area. And we are also multiplying, basically dividing by d of u minus l, where u is basically supremum of gx minus infimum of fx, where l is infimum of gx minus supremum of fx. So okay, so this should be fx, obviously this should be f of x, right? So this is what we have in mind. Now for that, what we have here is this. We can say the upper sum of g with respect to p prime minus the upper sum of f with respect to p prime would then mean right. And here obviously v is supremum of s belongs to p prime of v of s. So v here denotes basically the supremum of the set of the subrectangle S, which belongs to p prime, obviously, of the volumes of S. So v represents the highest number of volumes here, where v is defined as follows. We use v here, like this. Okay, so it's basically the least upper bound of the volumes of the subrectangles of p prime. Similarly, what we can also do is as follows for the lower sums. Where we also find that v is the supremum again. So basically what we want to understand here is we wanted to find u of l minus g of l, right? So ultimately we can show that u of g minus g of p prime, so the upper sum of g with respect to p prime minus the lower sum of g with respect to p prime is equal to this definition limits, right? So upper sum of g of p prime is basically summation over all rectangles right, and from this above 2 what we can see is that u of g comma p prime and minus u of f comma p prime is basically this is less than equals to this, and this is less than equals to this. So obviously this would be less than equals to like this. So u of g comma p prime is less than equals to this part only, less than equals to u of f comma p prime plus d into 2 to the power n into uv, right? and this part is greater than equal to right. And so since it's a minus, so this part is greater than equal to this part, so minus of this should be less than equals to minus of this part, right? And now we can write this as follows: u of f comma p prime minus l of f comma p prime plus 2 to the power n dv into u minus l, and this part is again less than equals to epsilon by 2, so it's epsilon by 2 plus 2 to the power n dv u minus l. But we know that this v is less than this volume, v is less than a particular thing, so what we can do is this epsilon by 2 plus 2 to the power n into d into u minus l, and v was less. If you can go above, what we can see is that v is less than epsilon by 2 to the power n plus 1 d into u minus l. So epsilon by 2 to the power n plus 1 into d into u minus l, right? And therefore this cut off to give you a t, and this both cut off, and what you get is epsilon by 2 plus epsilon by 2 equals to epsilon. So therefore it is integrable. Therefore g is integrable. And now it is obvious that integral of f is equals to integral of g. So you see that this kind of problems make a lot of sense when you try and implement them with the functions from Riemann integration. And obviously since you have multivariate calculus here, it becomes a little too messy, but obviously that can be overcome very easily. So that would be all, and you will see the embedded video after this, which you could have seen in the first as well, because I've already mentioned it, and that would cover the basics of integration if you need any, in order to find out how to do this integration and summation things at the first hand. So integration would be divided into a lot of parts, and we will try to cover the basics, but remember your basics from differentiation first. So I would just write it down in a table, and after that I will try to explain all of this to you. So in this table, what I'm trying to do is write a function on the left hand side and an integral on the right hand side. So note that in the first two entries, the function x to the power n when differentiated will always give you n into x to the power n minus 1 for all of the n's. But for integration of x to the power n, what it will give is x to the power n plus 1 divided by n plus 1. So as you know, in derivative, the exponent comes down as a coefficient, and then the exponent is reduced by 1. So the opposite happens in integration. The exponent is increased by 1 and then whatever the increased exponent is, that is divided. So that's integration. And as you can see in the second case, x to the power minus 1, that has a derivative of minus 1 upon x square, and the integral is log of x. That is why it's a special function. So remember that 1 by x when integrated will always give you log of x, because if you remember, the derivative of log of x is just x to the power minus 1, and integral is basically the opposite of derivative. So whatever you see in the integral column, if you differentiate that, you will get back the function. So like these are the basic derivatives that we need to know now, and integrals which we should start off. But what I need to focus here is that in integration, it's not actually as simple as it was in derivative. By using some rule or something, we can always evaluate, right? So derivative of a function can almost always be evaluated if the function is composed of only elementary terms, because we do know the derivative of all the elementary terms, right? But in case of integration, it may also be possible that for a given function there is no such integrand in terms of elementary functions. So an elementary function may not always give you answer, right? So this could happen. So let us begin our journey and let us know some of the basic rules. Integral of a function f of x is written as, so we will denote by capital I an integral, and the integral of function fx, obviously the variable is x, will be denoted by fx into dx. So this dx term is something which we have used, you have seen in derivative where we use the term d of dx, d by dx. So here we rather multiply with dx. Dx is called an infinitesimally small element of x, and this helps you to integrate. So this is something which should always be present in an integral, and thus the integral sign makes sense, right? So if we were to integrate, suppose x dx, then we would only focus on the function x, because dx is always present by far, and as you know, this comes in the category of the first kind of functions where x to the power n and n is not equals to minus 1. So the answer would just be, since the power is 1 here, the answer would be x to the power 1 plus 1 by 1 plus 1 plus c. So whenever doing an indefinite integration, now indefinite integration is something where you do not have limits, see. So when you do a definite integral, you will have some numbers or some functions as limits, as a lower limit and as upper limit, because you always integrate up from in some interval, okay, and you write the endpoints of the interval here. But when you are doing indefinite integration, we always add a plus constant c, because when you differentiate this thing back, you should get the function, right, which you will get, but it's not entirely sure that only this function would give you, because any constant, even if was added when on derivative, will become 0 and will give you the same function. So for any constant c, this equation becomes true. So since we do not exactly know what the constant was, so we just put a plus c. So this answer would be just x square by 2 plus c. Imagine that x square by 2 plus 5 or x square by 2 plus 2, both of them would give you on differentiation the value of x, right? Similarly, if you were to do 1 by x dx, the answer would just be ln of x plus c, right? Okay, so we do know about these basic differentiations, and let me now iterate some of the facts. Integration of f of x plus g of x dx So when there are two functions added, we can obviously write them as integration of, it's actually plus minus, even for minus it works, integration of fx dx plus minus integration of g of x dx. Okay, if there is any constant c such that you have c into f of x dx, where c is independent of x, c is just a constant. When I say constant, I mean it is independent of the integral variable. It will just give you c into integral of fx dx, right? So these are the two things we shall remember. There is not a hard fast rule for integrating product of two functions or division of two functions, but what we do have is something we will learn in the later chapters, which we call integration by parts, which is not really a rule which will readily integrate anything for you, but yes, it does help you integrate a lot of functions. So how do we actually integrate? So there are some ways to do that, and we will learn those methods slowly one by one. So let us integrate some of the basic integrals first. Let me write down the integrals. So let us try to evaluate all three of them. The solution for 1, as you can see, it's just e to the power 2x dx. What we can do here is we can write e to the power 2x dx equals to e to the power 2x divided by 2 plus c, right? Similarly, for number 2, what we can do is we can write integration of sine of x plus cos of x dx, and we can write integration of sine x dx plus integration of cos x dx. As I already mentioned, that we can separate the two functions which are in addition or subtraction form and integrate them separately. Okay, so as we have learned, the integration of sine x would be just minus cos x dx, there is no dx because it is out of the integration, plus integration of cos x is just sine x. And you might wonder that there should be two constants corresponding to both of them, but we do not really care, because since they are constants, we can just write a plus c at the end of the whole integration, because it doesn't really matter, because c is unknown, right? So whatever c1 here and c2 here plus would give, probably capital C would also give you the same result. Even if you write two constants, it can be absorbed into one, right? So this is the answer for second one. And for the third one, it's try e to the power log x plus x dx, but we observe that e to the power log e of x, which is the natural logarithm, is just x. So x plus x dx, which is basically 2x dx, and we can see that the constant 2 comes out and it's just x dx, and x dx has a form which is x squared by 2, and there would be a plus c outside. This would mean you will have the integrated as x squared plus c. This is your answer. So these are just the basic applications of the direct formulas. So this is not at all integration, it's rather like we are trying to revise some of these formulas and some of these formulas from this table, right? But now let us come to the actual part of integration. So when integrating, obviously you are trying to find a function which when differentiated will give you back the integral, right? So if you're trying to integrate some fx dx and what you get in answer is a function g of x, what you actually mean is when you differentiate g of x, you should get back the function f of x, right? Or in other words, there exists a function gx such that g prime x should be equals to f of x dx. This also means that when you have an integral of a differentiation, that is, if you have integral of f dash x dx, where f dash x is already the derivative of fx, it would just give you fx back. This is what integration means, because it's just the opposite of differentiation. Okay, so this is very important to understand, that obviously when you are trying to integrate a function, you are trying to find another function which when differentiated will give you back the integrand. Now let us go to some of the topics. Method 1, and by far the most important method, which we are going to learn extensively in this video and in future videos. Rule of substitution. Rule of substitution, right? So how do we find this? How do you find the rule of substitution? So consider an example. Let us say we are trying to evaluate the integral I equals to 2x e to the power x square dx. Now this is not a part of any of the elementary functions that you have seen, but it's rather a composition of two. And e to the power x square, remember that e to the power x's integral is e to the power x, but in case of differentiation of e to the power x square, you could have just used the chain rule, right? But it's not so simple here in integration, because there is no definite rule for integrating e to the power x square dx. Neither there is for integrating x into e to the power x square dx, right? So we need to make our way out of it. So what we do is we try to see what is the anomaly here. So if it were e to the power x only, it would have worked, and if this x were somehow magically gone, so this x squared term needs to be substituted. How do we do that? So we just substitute it. So let us introduce a new variable, which is y, and which equals to y equals to x square, right? Now only y equals to x square would not give you an answer, because you cannot just substitute it as y. That is why what we do here is we use d of y, we differentiate both sides to find dy by dx. So differentiate y in terms of x to find 2x, but then take this dx to the other side to find dy equals to 2x dx, right? And then you can see that this integral is basically equals to dy into e to the power y, which is just e to the power y plus c, or e to the power x square plus c. So this is the way we will try to do all the problems, and from the next section forwards we will be doing a lot of problems in rules of substitution. This is just an introductory video, and in this video, as I have said, we will try and do problems on methods of substitution, and we'll try to do as many problems as we can so that we understand method of substitution in a more clear way. But notice that this lecture obviously requires you to have a little bit expertise on differentiation, because as method of substitution is completely dependent on derivatives, because every time you are going to substitute a variable for some other variable, what you're going to do is to find the derivatives of both the sides and use the differentiation. And you also need to realize what derivatives or what substitutions are we going to make, so that the integral may be reduced to a simpler one or a more elementary one. That is the entire goal. So let me give the heading. So method of substitution. Okay. So in this method, let us try and understand what to do by choosing some of the problems. Let us say we have a problem x plus 4 whole cube dx. Now this problem can be solved in multiple ways. The first way will obviously being you would try to evaluate this x plus 4 whole cube as a trinomial. Like what you can do is use the formula for a plus b whole cube and use it as x cubed plus 4 cubed plus 3 into 4 into x whole into 4 plus x, and what you would get is x cube plus 4 cube plus 12x into 4 plus x, right? So you can break it down as x cube plus 64 plus 48x plus 12x square, and then you can integrate all of the terms separately, because all of them are just constant times some power of x, and we very well know that the integration of any power of x can be found out, because integration of x to the power n is simply x to the power n plus 1 by n plus 1 plus c, right? So obviously this is one method to do, but integration makes it a lot simpler for us, because when we use the method of substitution, what we try to do is we do like this: we substitute y equals to x plus 4. Okay, now when we do the derivative on both sides, what we get is we get dy equals to, now the derivative of this x plus 4 with respect to x would be equal to 1 plus 0, right, because the derivative of x is 1 and the derivative of 4 is 0 dx. So what we do get is dy is equal to dx, right? So what we are trying to do is, when we are trying to convert the whole integration from a variable of x to a variable of choice y, we also need to find the dy in terms of dx. So the dy would be in some function of dx. Here it is equal, which is another case, which would simplify our integral like this: x plus 4 whole cube dx would just be equal to y cube dy, because you see we have substituted. Now it might seem a little bit dumb, because well, you do see that we could have just simply found out x to the x cube dx, right? But it's not the case, as you will see. Now the integration of y cube dy is just y to the power 4 by 4 plus c, and this can be done because the variable of integration is dy here, right? And now after you've got the answer, you put back all the substitutions. So y was substituted as x plus 4, so what you do is x plus 4 whole cube by 4 plus c, which is the answer, right? So okay, so this makes x plus 4 whole cube by 4 plus c, and these are the two ways that we can evaluate this integral, right? Okay, so let us move on to another example, which would be a little bit more trickier, or maybe a bit tad harder than this one. Let us evaluate sine of ax plus b for real numbers a and b. Okay, for real numbers a and b. Okay, so how do we do that? Well, obviously in that case also, what we are trying to do is we are trying to substitute this thing ax plus b, because were it only sin x dx, it would have been easier, right? So let us name the integral as I, and let us substitute y equals to ax plus b. Now, as in the previous problem, what we are going to do is we are trying to differentiate both sides to find an expression for dy in terms of dx, right? So differentiating both sides, we get dy is equals to a into dx, because the constant b would disappear, and a into x's into differentiation is just a, and we have an extra dx always, as I told you. So dy would be a dx, or in other words, dx should be equal to dy by a. Okay, now this would turn our integration something like this. It would be sine of y, because ax plus b is y, and dx would be dy by a, and this would give you 1 by a sine y dy. Now we know the integration for sine y, it is just minus cos y, so the answer would be minus cos y by a plus c. And it's time to put back the variable which we substituted, which would give us cosine of ax plus b by a plus c, which is the answer for our integration. So as you see, like this kind of equations are this kind of integrals can be solved by using simple substitutions, but obviously there are harder ones. So let us try to find out another integral. Evaluate integral of 1 by 1 minus 2x dx. Now what does this resemble of? Firstly, because the simplest way we can evaluate an integral or to find out what to substitute is to find out the most recent or the closest integral which it resembles to. So as far as I can tell, this resembles to something like this, right, whose integral we known as ln of x. So if we can somehow transform it in this form, that 1 by some variable and d of that variable, we can do that. An obvious way to do this is to substitute 1 minus 2x, and since it is linear, we substitute y equals to 1 minus 2x. Now y equals to 1 minus 2x would give us a pretty easy way to evaluate this integral, because when you differentiate both sides, what you get is dy equals to minus 2 dx, right? And this would give you dx equals to minus dy by 2. Using this I should be equal to 1 by 1 minus 2x is just 1 by y, and dx is just minus dy by 2, right? And so the constant minus 1 by 2 comes out, and we have 1 by y dy. Now this would give us minus 1 by 2 ln of y plus c, and it's time to put back what we have substituted, which gives us minus 1 by 2 ln of 1 minus 2x plus c. So you understand that we are, in every problem, what we are trying to do is we are trying to reduce the integral by using some magical substitution, or rather a rational one once you try to get the hang of it, to reduce it to an elementary integral we know of, and then evaluate it directly, and then put back the value of the variable once it is out of the integration to get back our result. So this is what we call the method of substitution. We'll see a lot more examples in the coming sections, obviously. So the general version for this one would be, the general version for this type of integral is dx by ax plus b, and you can evaluate it. So let us name it as I. Substitute y equals to ax plus b. Now when we substitute y equals to ax plus b, we can have dy equals to a into dx, right? Then I should be equal to integral of dx is dy by a, so put a 1 by a outside, dy here, and this should be y. So this would give you 1 by a ln of y plus c, and if you put back the value, it would give you 1 by a ln of ax plus b plus c, which is the answer. Okay. Now next example what we can get is something like this. We can try and find out some of the basic theorems regarding this, like so this one is a tad harder, but what I'm going to teach you in this, in regard to this problem, would be something that you should remember in your way along. So this type of an integral is not something where you just magically find the substitution, but rather you literally look for something. So that something is determined by the following theorem. Theorem says that if you have f of gx into g prime x dx, this is the form of the integral, which as you can see is the chain rule. Then this is equal, then this is basically equal to the integral of f of gx d of gx, or you can say this is equal to f of y dy, where y equals to gx. So you just need to integrate the function f. If the function f is integrable to you in an elementary form, you would be done, right? Okay. So what we are trying to find is, if we can find something, some function which is a function of something, and the derivative of that function is already given along with dx, we can directly substitute that function. Why? We can see why. So given integral is I equals to 2x into root over of 1 plus x square dx, and we can substitute y equals to 1 plus x square. Why are we doing that? Because see, I realize that the integral of 2x into root over 1 plus x square can be solved if we were to eliminate this root over 1 plus x square thing. So when I substituted y equals to 1 plus x square, I saw that the derivative of 1 plus x square is just 2x, which is given along with dx. So 2x dx would be substituted into a single dy, which is what we wanted, which is basically the form of this function, right? So the derivative of 1 plus x square is already given outside. So when we do dy, what we get is 2x dx, and that is helpful because this turns into root over y into dy, where 1 plus x square got to y and 2x dx was written as dy. And this is an easy one because this is just y to the power half dy, and using the rule you can find it as y to the power half plus 1 divided by half plus 1 plus c, which is basically y to the power 3 by 2 into 2 by 3 plus c, which is the answer, right? So this is the integral and this is the answer, and we can just substitute back to get our answer in terms of x, obviously. So it is basically 2 into 1 plus x square to the power 3 by 2 whole by 3 plus c. This is our integral, right? So this type of integrals can be solved, but you need to be a bit cautious about them. So let us do another one. Evaluate dx. So we want to evaluate 4x by root over of 2x square plus 1 dx. Again, it should be noted that ddx of 2x square plus 1 is equals to ddx of 2x square plus ddx of 1, right? And ddx of 2x square is just 2 into 2x, and ddx of 1 is 0, which gives you 4x. So you see that 4x is already present. The derivative of the term of 2x square plus 1 is already present. And if that is so, what we can do is we can substitute y equals to 2x square plus 1, and thus we see that dy is equals to 4x dx, and this would turn our integral into something like this. But this just only means that it's y to the power minus half dy, and using the rule we can write it as minus half plus 1 by minus half plus 1 plus c, which is basically y to the power half, and this becomes 2 because it's a half in the denominator. And we can substitute back our answer to find it's just 2 into root over 2x square plus 1 plus c. If you differentiate this using the chain rule, you would find that the answer is basically 4x in divided by root over 2x square plus 1, which is amazing because differentiating something is very easy, while integrating something is insanely hard, just because of the methods or the ways you have to look for, right? Okay, let's do another one. Evaluate sine of root x by root x dx. Now again in this one, as you can see, the only portion that is not going with the integral is the root x inside the sine, right? And we are kind of sure that whatever else is present in the integral should be the derivative of that, right? So let's see. We observe ddx of root x is just equal to ddx of x to the power 1 by 2. Now we have learned previously that the ddx of x to the power something is just the coefficient comes out, so the coefficient comes out, and the coefficient the power comes out as a coefficient, and the power is reduced by 1, which means it is half into x to the power minus half, or in other words 1 by 2 root x, right? So if we were to differentiate, what we would get is something like this. Let y equals to root x, then dy should be equals to dx by 2 root x, right? But we see dx by root x is also present, so what we get from this equation is dx by root x should be equals to 2 dy, and we can absolutely put this to get the integral as for I equals to sine of y, because root x is y, into 2 dy. Since 2 is a constant and is in multiplication with the rest of the integral, it comes out, and we only have to integrate sine y dy, which is just minus cos y. So it's minus 2 cos y plus c, and putting the value of y back, what we get is minus 2 cosine of root x plus c. This is the answer, right? So you see, like, this kind of integrals can be solved, but then again we have to be a bit cautious. So let us solve a lot more problems. Example 7. I will try to do this as much as I can so that you get the idea of method of substitution completely. And if you have any trouble in evaluating derivatives, please go back to the last videos to find out how to evaluate a certain derivative or how to do complex derivatives as well. Okay, so example 7, evaluate integral of 2x e to the power x square minus 5 dx. So let us denote the integral by I, so that I is equals to 2x into e to the power x square minus 5 dx. Note that now again in this integral we are trying to see that since the derivative of x square minus 5 is just 2x, what we can do is y equals to x square minus 5, which should give us dy is equals to 2x dx, right? Then on substituting, I is equal to e to the power y, and the 2x dx becomes dy, right? And you know the integration of e to the power y is just e to the power y plus c, and you put in the value which was x square minus 5 plus c. So this type of integrals, if you find the derivative of a term directly present inside the integral, try to substitute for that term so that you can reduce it into a common integral or an integral that you know of, okay? Because only then would it be easier for you to find out what to do. So we will continue our examples, but first let us learn one more thing. Let us do one more example, then from the next video we shall also do all the other indefinite integrals that we are required to do in the method of substitution, but also we will do some of the definite integrals, and we will learn how to do the definite integrals as well. So let us do this. This would be example 8, right? Yeah. So we'll continue from example 9 in the next video. So this would be the last example for this video. So let us do this problem where we have integral of cosine of x dx by 1 plus sine x. So this one looks a bit more tedious than before, but note that ddx of sine x is just cos x, right? So as we can see, cos x dx is present in the numerator and 1 plus sine x is in the denominator. So if derivative of sine x is cos x, then derivative of 1 plus sine x should also be cos x, right? So rather than going for the substitution y equals to sine x, what we can do is we can directly go for the substitution 1 plus sine x, then let y equals to 1 plus sine x, and from that we get dy is equals to cosine of x dx. This would give us our integral as y equals to integral of dy divided by y, which is just the integral. This integral is evaluated as a natural logarithm, right? So ln of y plus c, and remember the y is always positive, so it's rather a modulus. So the answer by putting back the value of y would be ln of 1 plus sin x plus c, which is the answer. So these are by far right now the easier parts of the integral, but we shall do some more integrals to find out how to do them, and then we shall move on to the next part where we learn how to do methods, integration by substitution, and some other methods for evaluating indefinite integrals, such as, let's say, the surds and the radicals. And finally we can move on to definite integrals, which are of utmost importance, which is why you are learning indefinite integrals, right? So let me introduce you to you the new concept, which is integration by parts rather, and then we can continue solving problems which are mixed from both the sections. So integral by part, which is also known as IBP in short. So as the name suggests, it is actually a rule to find out integrals of the form where you have two functions fx into gx dx. What we do here is we try to name or label the functions as function 1 or function 2, and once we do that, we can have an easier rule to find out the integral in terms of another integral, which might be easier to solve. So as of derivatives, it does not obviously give you a direct answer, but it rather gives you a newer integral which might be easier to solve, and we have a rule for it. The rule is something like this. The rule is called ILET. I for inverse functions, L for logarithmic functions, A for algebraic functions. Algebraic functions means function of polynomials like x cube, x to the power 4 plus 2, and something like that. Logarithmic is involving log, inverse is involving sin inverse x, cos inverse x, tan inverse x, like that. So they're inverse trigonometric functions. T is for only trigonometric, and E is for exponential. So why is this order important? This order is to choose the function that you choose which is higher up the list, which is like if the function, there are two functions in multiplication form, which is one of them are inverse and another one is algebraic, then you would have the inverse function as the first function and the algebraic as the second function. So if the function is higher up on the list, you would name it as function 1 and the other one would be function 2. So let us name here fx as function 1 and gx as function 2. Then what it gives you is function 1 directly comes out into integral of function 2 dx minus integral of derivative of function 1 into integral of function 2 dx multiplied by derivative of function 1 and the integration of this whole. So this is how it works. So you take the first function and you multiply it by the integral of the second, and you subtract from it integral of derivative of the first function into integral of the second function. So let us take some examples so as to understand how this works. Example 1. Let us find out the derivative of x log x dx. Okay. So identify x is an algebraic function, right? ln x is logarithmic. So which one is more up the list? Obviously L, right? So L should be treated as the first function and x should be treated as second function. So denote the integral by I. Integral by I, and what we do get here is I equals to integral of x log x dx. Given that log x, we are denoting log x as first function, x as second function, which means we should have first function into integral of second function minus integral of derivative of first function, which is just 1 by x, into integral of second function and the integral of the whole thing, right? So integral of x dx is just x square by 2, right? So it should be x square ln x by 2 minus, we have already found the derivative for log of x, which is 1 by x, and again integral of x is x square by 2. So in this inner integral you do not need to include the constant plus c, so we are basically trying to just find the integral and accept the constant. So 1 by x into x square by 2 dx, and as we can see this becomes x square ln x by 2 minus integral of this x is cut off, it's x by 2 dx, which can also be evaluated because x square log of x by 2 minus this is x square by 2, so this is x square by 4. Now we can include a plus c to complete our answer. So x log x could not be evaluated otherwise. The only way is to guess the function whose derivative is x log x, which is kind of impossible. So we do not really need to follow that strategy, obviously, but this would give us the answer, right? Okay. So let us try to find out some more problems. For the next problem, what we do need is this: d dx of tan inverse x is equals to 1 by 1 plus x square. We are going to prove it, but first understand that since the derivative of tan inverse x is 1 by 1 plus x square, this also means that integration of 1 by 1 plus x square is equals to tan inverse x plus c. Okay, and how do we prove it? Okay, so let y equals to tan inverse of x, then what we see is x should be equal to tan of y, right? And what we are trying to find is dy by dx, so let us see how to find that. And the derivative of tan y is sec square y, if you remember it from the derivative section. So differentiating both sides, we get dx equals to sec square y dy, and sec square y is just 1 plus tan square y dy, and so dy by dx would be equals to 1 by 1 plus tan square y, but tan y is just x, so it is just 1 by 1 plus x square, right? So the derivative for tan inverse x, which is dy by dx, is 1 by 1 plus x square. Proving it, and all the other inverse functions can be proven in the same way, and corresponding to that we can find this integral. Evaluate integral of x to the power 4 by 1 plus x to the power 10 dx. Now at first glance, obviously that we want to eliminate the or substitute for the denominator, but we see that the derivative of 1 plus 1 x to the power 10 is not x to the power 4 dx, right? Or not any constant multiple of x to the power 4 dx rather. But what we can do here is denote the integral by I, then what we get is this: capital I is equals to integral of x to the power 4 dx divided by, and we can write x to the power 10 as x to the power 5 whole squared, because in that case what happens is, if we substitute y equals to x to the power 5, what we get is dy is equals to 5 into x to the power 4 dx, right? And what we want is the value of x to the power 4 dx, so therefore x to the power 4 dx should be equal to d of y by 5. So our integral becomes I equals to integral of, this thing becomes dy by 5, and the denominator just becomes 1 plus y square. So the taking the constant outside, we get 1 by 5 dy plus 1 by y square. Now since we already know the derivative integral for 1 by 1 plus y square is tan inverse y, But if we hadn't known that, what we could have done is we can use trigonometrical substitutions in problems where we have something of the form 1 plus x square or 1 plus y square in the denominator or in the numerator. Because if you substitute, and remember, obviously you can make as many substitutions as you can. There is no rule of making only a single substitution for a single integral. As you can see, I am going to make a second substitution now. I am going to substitute for the substituted variable itself. So substitute y equals to tan theta, where theta is another variable. Then dy would be equals to sec square theta d theta, if you remember the derivative of tan theta, and sec square theta is just 1 plus tan square theta d theta. And as you know, 1 plus tan square theta is just 1 plus y square d theta. So therefore, taking this on the left hand side, we get dy by 1 plus y square equals to d theta. So this whole thing becomes d theta, right? So therefore, I equals to integral of d theta by 5, and integral of d theta by 5 is just theta by 5 plus c. But theta, as you know, if y is tan theta, then theta would be tan inverse y. Then the answer would be tan inverse y by 5 plus c. But we also need to put back the value of y, which we substituted as x to the power 5. So the answer would be tan inverse x to the power 5 whole divided by 5 plus c, which is our answer, right? Okay, so this is another problem, and let us do another one. This one would be from the section of IBP. So obviously, whenever you're facing or you're in a situation where you are in exam or some problem solving session, you might not be given the topic, right? So you might have to figure out on your own how to do a certain problem of integration. If it's a definite integral, or even if it's an indefinite integral, you might have to substitute for something. You might have to do integration by parts. So there are various ways to do an integral, and you need to figure out which way works for you, which way actually solves the integral, because other ways might actually make you go round and round and come back to the same integrand again, right? So let us evaluate x sin x dx, and after that we'll do a more complicated version of this. So denote by I the integral, and whenever we see functions which are product of two different kinds of functions, we try to remember our eyelet rule, where we obviously know which one to take first function and which one to take second function. So in the eyelet rule, as you can see, eyelet, the algebraic function comes first after the trigonometric function. So algebraic function should be part 1, function 1, and the trigonometric one should be function 2, right? Then we have I equals to x into integral of sin x dx minus derivative of x, which is d dx of x, into integral of sin x dx, and whole thing is dx here, right? Now integral of sin x is minus cos x, so this is minus x cos x dx, minus x cos x, minus d dx of x is just 1, and integral of sin x is again minus cos x, right? Then as you can see, it simplifies considerably into minus x cos x, and this minus make it a plus, and 1 into cos x is cos x dx, and you do know the integral for cos x dx, which is just sin x, right? So the answer is x minus x cos x plus sin x plus c. So this integral is something which just comes back around its own, because the trigonometric functions, the sin x and cos x functions, generally they come back around its own when you integrate them enough number of times. So for example, they have a period of 4 on integration. So if you integrate sin x 4 times, you will actually get the same result. So let us try to find out something else here. Next problem would be integral of e to the power x sin x dx. Now this is a problem where you would know why the denote by integral I is of paramount importance. Okay, let's see. Denote the integral by I. Then what we have is I is equal to e to the power x sin x dx. Now if you remember in the rule I late, e that is for exponential functions that came last. So obviously e to the power x is going to be the second function here and sin x is going to be the first function. So applying IBP or applying integration by parts, what we have is this: I is equals to sin x into integral of e to the power x dx minus ddx of sin x into integral of e to the power x dx dx, right? So what we do get is integral of e to the power x is just e to the power x, so it becomes e to the power x sin x minus differentiation of sin x is cos x, so cos x into e to the power x dx. Now this is another integral, so again we apply the same integration by parts technique with cos x as the first function and e to the power x as the second function. Notice how we have to do integration by parts twice here, and we are doing it as you will see why. It becomes cos of x into integration of e to the power x dx minus the integration of ddx of cos x, and as you know integration of e to the power x dx is just e to the power x. I'll just write e to the power x dx here. So it becomes e to the power x sin x minus e to the power x cos x, and ddx of cos x is minus sin x, and minus becomes plus. It becomes e to the power x sin x dx. And if you take it away from the bracket, what becomes is e to the power x sin x minus e to the power x cos x minus integral of e to the power x sin x dx. But notice that this is the integral that we started with, right? So this is denoted by I, which is a variable. So this becomes e to the power x sin x minus e to the power x cos x minus I, and on the left hand side we have I. So solving for I, what we get, solving for I, we get 2i equals to e to the power x sin x minus e to the power x cos x. Therefore I is equal to e to the power x whole into sin x minus cos x by 2, which obviously there is a plus c, which is the answer. So this is one of those integrals where you have to do integration by parts twice to get the answer. So this is a problem where we have basically the integral coming back on its own, and then we have to solve it like that. So this happens a lot of times. So let us do another problem. This one would be a bit tad harder than the last one because of the concepts involved. Evaluate integral of sine of log x plus cos of log x dx, right? Now obviously what we want to do here is, first, as this is not any function that we can be reminded of, this is not any elementary function, neither does it have substitution that is very clearly visible. So obviously the derivative of log x is also not present, right? So naturally the first thing we would like to try is to substitute for log x and see if that makes any difference, right? So obviously I is equals to integration of sine of log x plus cosine of log x dx, and substitute y equals to log x, which will give us dy equals to 1 by x dx, right? Therefore this integral would become, and from this you can see that dx is basically equal to dy into x, but we need it in terms of y, so x is basically e to the power y, so dx is basically e to the power y dy, right? So the integral becomes sine of y plus cos of y whole into e to the power y dy. And this is time to introduce a new theorem, or rather a lemma, which is helpful sometimes. So lemma: for a differentiable function f of x, if I is equal to integral of e to the power x into f of x plus f dash x dx, then the integral is I equals to e to the power x into fx plus c. So if you have an integral in this form, the answer is simply e to the power x into f of x. So the proof is necessary, so we shall do the proof here. We start with the integral, given integral, and we shall see why this lemma is important in solving this problem, this particular problem. So given integral is I equals to e to the power x whole into f of x plus f dash x dx. Now let us separate it into two different parts, that is e to the power x into f of x dx plus e to the power x into f prime of x, or derivative of fx dx. So let us try to break down this second integral. Name this integral as b. So b equals to integral of e to the power x into f prime x dx. If you apply integration by parts here with e to the power x as the first function and f dash x as the second function, what you do get is e to the power x into f dash x dx minus derivative of e to the power x is just e to the power x, and integral of e to the f dash x, and then a dx outside, right? Now we know that the integral of a derivative is just the function itself, so it just becomes e to the power x into f of x minus this becomes integral of e to the power x into f of x dx, right? So if we put the value of b there, we see that I is equals to integral of e to the power x f of x dx plus b, where b is our desired integral which we have just evaluated using integration by parts, and which becomes e to the power x into f of x dx plus e to the power x into f of x minus integral of e to the power x into f of x dx. And as you can see, these two integrals cut off because they are exactly the same thing. So the answer is just e to the power x into f of x, which is the answer for the integral. Now in our given problem, in our given problem, we have I equals to integral of e to the power y, it was, into sine y plus cos y, right? So let f of y equals to sine of y, then f dashed y would be equals to cosine of y, and therefore I equals to e to the power y into f of y, which is sine of y, and cos y is the derivative, so f dashed y, right? And from the lemma we see that this is basically equals to e to the power y into f of y plus c. Putting back y, we get e to the power, and what was y again? Y was log of x, right? So we get e to the power ln x into f of ln x plus c. Now e to the power ln x is just x, and f of ln x is just sine of ln x plus c, which is the answer to our integral. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.